Coenraad Mouton, but is also a part of the Multilingual Speech Technologies Research Group at the Northwest University, and he will be presenting his piece on stride and translation invariance on convolutional neural networks. Over to you, Koen.
Thanks a lot, Arthur. So let me just get a timer here. Okay. Everyone can see my screen, right?
Yes, thanks, Koen.
Okay. I've already been introduced. I'm just going to jump right into it. So just a quick overview. We provide a theoretical overview of translation invariance and what contributes to it in CNNs, a slightly different perspective than the paper Christiaan just presented. And then we propose a novel theoretical perspective surrounding how stride and filtering relates to translation invariance. And then we empirically test this theoretical perspective. So firstly, translation invariance basically is just if a model's output is unaffected by shifts of the input. It's commonly incorrectly assumed that CNNs are invariant to translation, and we know that they aren't. But while they aren't necessarily invariant, CNNs can be equivariant. So equivariance is just a property where a shift of the input results in an equal shift of the output. So a quick example of this, if you consider pooling and the convolution operation, you'll know that they are translational in nature because they are shifted over the input to provide an output. So intuitively, equivariance should hold. So here's just an arbitrary input and an arbitrary kernel. And here we have that input and then a shift by 1 to the right and shift by 2 to the right. And this column is the convolved output. So looking at these outputs, you see that they are exactly the same for the shifts, except that the output has also been shifted by the same amount. So shifting the input results in a one-to-one shift in the output. So where does equivariance fail in CNNs? Well, equivariance only holds for dense pooling and convolution, meaning if you're using a stride of 1. Subsampling, meaning using a stride greater than 1, breaks this property because subsampling disregards intermediary samples. So consider the exact same example from the previous slide, but this time with a stride of 2 when we're calculating the convolution. And you'll see that for a shift of 1, in this case, the outputs are no longer equivalent since intermediary information has been lost. But luckily, there's a third property, and we call this shiftability. So subsampling or using stride can essentially scale a shift if that shift is a factor of the subsampling factor, where the subsampling factor is just the total amount of stride you're using in your network. So if you have 2 layers with a stride of 2, that would be a subsampling factor of 4, 2 by 2. So to illustrate this, it's the exact same table from the previous slide, and you'll see that for a shift of 2, in this case, it's equivalent to a shift of 1. The output is equivalent to the untranslated output here. But notice that even though the output or the input was shifted by 2, the output is only shifted by 1. So this funny little property of subsampling actually allows it to kind of reduce and scale a shift of the input. So how does this relate to invariance then? So even if you have a fully equivariant network and your convolution and pooling outputs would be equivalent for any translation of the inputs, but this shift would still occur in the fully connected layer. So say this is your output feature map. For the fully connected layer's input, we flatten this into a one-dimensional vector. So obviously, shifting the input by 1 to the right would shift the output 1 to the right like this, and the same shift would occur in the fully connected layers. And as MLPs essentially have no spatial reasoning abilities, this shift can be very detrimental to their classification ability. So we propose that there are 2 things that need to be taken into consideration here. The first thing is signal similarity. So how much of the untranslated signal's output is still preserved after translation? Basically, how similar are the translated output and the untranslated output? But also signal movement. So how far the translated output has been moved from the original position of the untranslated output, meaning how big is that shift when it gets to the fully connected layers. So obviously you want signal similarity to be as high as possible, but you also want signal movement to be as low as possible. So with a fully equivariant network, you get perfect signal similarity, but you also, your output's also shifted in a one-to-one ratio with the input. If you use strided filters, then you can reduce signal movement, but you lose some signal similarity. So this, luckily, is where local homogeneity comes in. So this is just a term we use to refer to local regions being very similar to each other. So separate pixel values in a local region being similar. So here's an arbitrary example to illustrate this. So here's just an input that is homogeneous in accordance with a subsampling factor of 2. So you'll see every pixel value essentially just repeats. Shifting this even and then subsampling that output, you'll see that it stays equivalent for any shift of the input. And luckily, this is exactly what pooling or another form of filtering does. It reduces the variance of the given input and thus provides more similarity between neighboring pixels. So then, if you're using strided pooling, you can improve signal similarity, you can reduce the signal movement by subsampling, and this should result in greater translation invariance. Okay, so on to the empirical. So how we measure translation invariance, slightly different than the previous paper that was presented. So we, once again, translate the entire test set, but we randomly translate each sample in the test set up to a maximum shift. Then the translated and untranslated test set is passed through the model, and then each sample's two 10-dimensional output vector are compared using cosine similarity. And then we just take the average cosine similarity across all these samples, so across the entire test set. Okay, so for the first experiment, we trained 4 3-layer CNNs on the MNIST dataset, and we also zero padded our input to be 40 by 40. So this allows space on the image canvas for translation. We also optimize all our hyperparameters, and all these networks can converge to 100% train accuracy. But it's important to note that besides early stopping, we didn't use any regularization, as this might influence our translation invariance results. So the setup of the architecture is as follows. We've got 3 convolution and pool blocks, and the convolution and pooling kernel sizes stay constant. The only thing we vary between the networks are the stride of these pooling layers. So for the first network, all of the strides are set to 1. For the second, we have a subsampling factor of 2. So the first pooling layer has a stride of 2. Then for the third network, we have a subsampling factor of 4. So we have a stride of 2 here. And for the second pooling layer, and then the last network has a subsampling factor of 8, where all the pooling layers have a stride of 2. So here are the results. On the x-axis, you see the maximum shift that the test set is subject to, and on the y-axis, the mean cosine similarity. So higher is better. And we see that the subsampling can drastically increase the translation variance. Our top performer here is a subsampling factor of 8, then 4, then 2, and then 1, or no subsampling. So clearly, subsampling combined with 2x2 max pooling for the MNIST dataset can greatly increase its translation invariance. So how about CFAR? Well, we trained 16 3-layer CNNs with the same setup as for MNIST, except this time we also varied the max pooling kernel size and the subsampling factor along with that. So here we have kernel sizes from 2x2 to 5x5 and subsampling factors of 1 to 8. So just, and these numbers are the mean cosine similarities for a maximum shift of 10 pixels. So just looking at the first row here, we see that actually increasing the size of the max pooling kernels didn't increase the translation variance at all. In fact, it had the opposite effect. And this would make sense, since it has a subsampling factor of 1, it means that these networks are all fully translation equivariant. And then looking, at the first column, we see that 2x2 max pooling really isn't enough to preserve signal similarity. And subsampling also doesn't help the translation invariance. But for 4x4 and 5x5 max pooling, we see that subsampling, reading it from top to bottom, does drastically increase its translation invariance. So since CIFAR10 is a less homogeneous data set, you need greater filtering before applying subsampling. And we see that our best performing network of all 16 is the 5x5 max pooling with a subsampling factor of 8. Okay, how does this relate to generalization? So these are the test accuracies for the networks that were just shown on an untranslated test set, so on the CIFAR10 test set. We see that in some cases, some subsampling and filtering does increase the generalization, but too much filtering or subsampling has the opposite effect. So looking again at this 5x5 column, for example, we see that each value is lower than for 4x4 max pooling, and our best performing network in terms of translation invariance actually has one of the lowest test accuracies, especially if you compare it to the 4x4 max pooling. So this leads us to the conclusion that there's a slight trade-off between invariance and generalization, as too much filtering or subsampling decreases your generalization, but increases your translation invariance. Okay, so in conclusion, subsampling, when combined with sufficient filtering, improves translation invariance in convolutional neural networks, but too much subsampling and or filtering reduces the test accuracy. Now, we had tested several other things as well, such as data augmentation, anti-aliasing, and global average pooling. I have some backup slides, but I see I've only got 30 seconds left, so I guess I'll just leave it there for some questions. Thank you.
Thank you, Kun. Is there any presentations? Sorry, is there any questions for him? Yes, Emil, I see you raised your hand.
This would be a question maybe to you and to the previous presenter, but would you say that testing in this way to see if what the translation invariance is a good way to determine if the model is overfitting or not? Because it may kind of make sense that if it's not able to see a 7 that's in the corner, but it's able to see a 7 that's in the middle, then it's very much overfitting.
Yeah, I wouldn't really say that. The reason being is that we are training on a training set, which isn't then representative of the test set that it's subject to. So if you're measuring its translation invariance, you're giving it translated inputs, where for the train set, especially for something like MNIST, every sample is very much centered. So I wouldn't exactly call that overfitting according to my definition. If you take the definition that generalization isn't just the accuracy on the test set and more like how it generalizes to other world, outside world examples, then I suppose you could call it a form of overfitting, but I'm a bit hesitant to use that word. As to the spirit of your question, can you measure the translation variance to determine overfitting? I wouldn't really think so. As we saw, there's a lot of funny things you can do to increase the translation invariance. And these do not necessarily directly relate to the generalization.
Are there any other questions? I don't think I see anything.
Okay.